Okay, welcome back. This is Laban Hester, and this is the ThinkSmith channel. Woo! So, this is the last video I'm going to be recording today. I've been putting it off, even though it was the first one I wanted to record, because I just don't know that I'll do it justice. This is the idea on quarks and all that. So I don't know if this would be like an overarching theory or anything like that, like if it would battle against string theory and whatnot. But essentially, this all boils down to the idea of what are quarks. Because we got all these particles, we got quarks, which supposedly make up particles, except for the particles that are not made of quarks. Pretty sure electrons don't contain any quarks. And so, like, you get down to the size where you're analyzing what a particle really is, and I feel like it's overcomplicated. And I could be just totally out there wrong on this. I'm wrong on a lot of things. In fact, most of the videos I make will probably be talking about something I was wrong about. But I think, for now, that I'm right about this. I'm open to changing my mind, but I think science has overcomplicated itself on accident. Maybe on purpose. I'm a little bit of a conspiracy theorist myself. Could be a little bit of elitism in there that makes it so. But I think a lot of the times we come up with terms for things in science so that we can all agree on a definition for something that we're looking at. We can be like, this is a quark, this is a particle, etc., etc. That way we can segregate it and know exactly what we're talking about. But I think that the further into science you get, the more it gets mired down by you have to know what this is to understand what this is, because you need moles for chemistry and all this stuff, and it gets so advanced that you can't explain it well to a toddler. And if you can't explain it well to a toddler, you don't understand it well enough yourself. Sorry, you understand, just you could understand better. And I feel like the scientific definition of particles and quarks and all that kind of sucks, because essentially it boils down to like a quark is a quark, and a quark is a thing that has, well, mass and spin and up or down and all this stuff. And excuse me, I feel like that isn't a very good definition. I feel like it's if we were the size of the moon and we were studying a forest on Earth, and I could tell you that it was made of trees, and I really pressed you, and then you told me that trees have leaves. But without knowing what a tree really is, that doesn't really mean anything to me. So here is what I think the basis of the universe is. Anything that has mass is where space isn't. I think that all particles are a vortex in space. And I think that the mass comes from displacement of space in that area, which explains things like gravity to a degree, where by displacing space locally, you have more space. Kind of like maybe like how bread rises in the oven. You fill it with holes, and now you have more of it. And what you have is denser. So, in that vein, I think that particles are whirlpools, and that we should be able to study them using models of fluid dynamics. I think a lot of forces can be explained as spatial motion, and that there are different ways that space can move and be manipulated. So, for instance, I think a lot of like magnetism can easily be compared to the way that the space is moved due to the whirlpool. And it can explain a lot of attraction and repulsive forces as in that light. So, for instance, I think that you could model like a basic atom by creating a little lab dish filled with water that had several whirlpools in it, and that these whirlpools and their interactions would give us great, at least metaphors for a lot of interactions. Like, for instance, there's a lot of things that we have names for in physics that just seem weird to me, like gluons, that don't have any mass, and yet they're a quark, and they only exist to hold things together, and I don't know, it just seems there's a lot of weirdness, and I feel like we're inferring a lot of things by modeling things in not necessarily the right way. Like, for instance, I think that it's a three-dimensional whirlpool, and I'm not even sure it's the entirety of the whirlpool. I think that there's something to be said that could be explored for a lot of that dark matter and things like that could be tied very closely with the fact that we're not seeing the entirety of the whirlpool. And that the displacement of the space in some extra dimensional direction would affect how much talking myself in circles here, but essentially that the height of said whirlpool and not just its width could somehow influence how much space is generated outside of it by displacement, and that a lot of like evidence for some things where like dark matter must exist because we've observed this place that has much more gravity and space, because much denser time space than it should have for the amount of matter. And don't get me wrong, that's kind of loose. The biggest thing I want to talk on is just the idea of the whirlpool as a model. So for things like a particle is made out of three quarks that all have their own spin. You usually have like two ups and two downs, and in general, I think that there's like a set amount of probably like common whirlpools, and those are based on sizes and then their spin direction, which would be telling for ups and downs. And unless they are an exact match in terms of their criteria of how that whirlpool works, whether it be the speed of rotation, their size, all that, that it just they can't cancel out, but they can interact, and that is how we get these larger things. So like a proton is supposedly made out of three quarks, and I would argue that each one of those quarks on its own is just an unstable whirlpool. But when they combine together, you wind up with this larger, more stable whirlpool that has a net spin based on its constituents, but that it's that displacement that gives it its mass. I would say that because all matter is formed from essentially couple different whirlpool sizes trying to attract each other and become more stable because they have less of a external flow that they're creating, that is the basis of matter, and that pretty much no matter is stable. Like the most stable matter would be destroyed matter. It's kind of iffy. Essentially, entropy is both a balancing force and the force that's destroying everything, because the steps to make energy equivalent across the universe are just really complicated. So, in this vein, I'll kind of go into how, like, because matter's a whirlpool, you can make matter. And there's a lot of hypothesis on making matter. Sometimes it seems like Google searches will say that we haven't done it, and other times they'll say that we have done it. The experiment that I'm kind of basing this off of is the shooting two gold atoms right next to each other and making like electron and a positron, or sometimes it's called a neutrino. There's a lot of, seems like we coin a lot of things as neutrinos, and that gets complicated as well. But in general, it seems like there's not too many kinds of quarks. Sorry, I'm getting sidetracked. So you can make matter, you just can't destroy energy. And waves in this case would be like light, and different accelerations causes a moving wave in space, and those waves can kind of get wrapped together to make a whirlpool. And if they're not stable, those whirlpools can then collapse back and create another light wave. And usually another quark or something. They usually have a lot of byproducts, but most of the time you end up with stable quarks or particles, because the easiest way to destroy them is with their counterpart. And in terms of the universe, I would be willing to bet that most of the antimatter is in its own antimatter section that's created stability. Either that or it doesn't exist. But like, hey, you would assume it exists, because to create matter you have to make two things. You have to make the electron, and you also have to make the positron, which is its opposite. And they're just the same size, same spin speed, opposite rotations. If they come together, they completely cancel out and it becomes smooth. Or, well, not smooth. It cancels out and turns back from a whirlpool and just into a wave. And then that wave shoots off somewhere. I'm doing a lot of rambling here. But what did I expect? Anyway, another point is, I think that you could probably kind of model out an atom. Well, not an atom, but like a particle, maybe a little bit more accurately, with the idea of somehow stacking a whirlpool. So there's a classic thing called the T paradox, where a denser fluid spun will create an upward vortex where you would normally think that it would go down. So I think that by stacking some different fluids of different densities and then spinning them, you could more than likely model out what like an individual particle looks like, if you could get the vortex to both go up and down in the same spot. I think that would be interesting study-wise, because maybe we could use some modeling of this to figure out what constitutes space. Because we're talking a lot about displacing space with something, and that makes mass, because there's no space there. So if there is no space there, and we already kind of call space nothing, then there has to be a second nothing that comes in and displaces the space. Maybe null or something? I don't know. But I think it would be interesting if through this we found out that space had a few constituent parts itself, like two fluids that were right at a boundary line, and that's where we exist. Uh, I do a lot of thinking about this. Just, I think it'd also be interesting exploring this to see if you could build a proton or something out of three different whirlpools and have them mesh together, and then you could add in a second smaller whirlpool and see if it spun around and explore the ways that maybe it kind of merges in and out, or the way that particles maybe touch each other on levels where they get wrapped together, and then you only later we have like quantum entanglement, but maybe on some level some of that happens at these deeper layers where they touch, but they don't touch at the mouths, the air water barrier. If you're thinking about like a sink drain whirlpool, is the top. So maybe that's kind of more of where we exist, is on that top layer, and that some of this quantum entanglement is things that happen at the bottom. For instance, if you look into like what happens with if you take a smaller whirlpool, it can, and a bigger whirlpool, it can be sucked into that big whirlpool and become part of it, which I think is kind of what happens with like protons. But also it can kind of get wrapped up around it, and it might even phase kind of in and out of that. And I think that that might explain some of the quantum doohickeyness going on. Furthermore, I don't know, a lot of things like neutrons seem weird to me too, because we generally, you think of particles, you think of electrons, protons, and neutrons. And protons are already kind of a composite of three distinct not neutrino, quarks. And they say the same thing about neutrons, that they have kind of these three distinct quarks. But then there's things like electron capture, where an atom is too large, so it sucks in one of its electrons, and that electron joins with a proton and it becomes a neutron, and then it shoots out a neutrino, which is the exact opposite of an electron. And that neutrino will smack into an electron and destroy it. And something I've been playing around with mentally recently is the idea of the structures that make up these individual particles. So if a proton can turn into a neutron by eating an electron, at some level you would think of an electron as part of a neutron. So, and I know that there's conversions and energy coming in and out that is outside of these particles and quarks, but to me it seems like the electron is part of that neutron, and that the neutrino is a part of that proton. So to me it seems like, obviously, you have an up quark and a down quark, and those are each like a third or whatever, or two thirds, and a proton has two of one and one of the other, and when it eats an electron it shoots out a neutrino, so it loses its down quark. I think it loses one of them which should be 2/3, but you get a whole one out. So some of that I think comes down to like maybe like spatial compression factors, because I think that like you can almost look at a neutron as being its own hydrogen atom on its own. Because if you just had a neutron, it would break down, it would release a wave of energy, it would decompress, and you would have a whole atom of hydrogen. So to me, it seems like there has to be some level of like pressure in the sun where low lying, I'm rehashing things that are already for the most part true, but low lying, like close to the core, very compressed atoms shoot up with like a plume of heat and get lodged into another atom. And that if that happens enough, it destabilizes. So you start with one proton and a neutron, and that's actually probably more stable than it was before. But then when you get two neutrons in there, that's fine. But the third one, okay, now you got too much going on. And so it shoots off its electron because it has a reverse pressure on it from all the spins. And a thing to think about with the pressure of the spins is that it's an external spinning of space that grinds against the spin of space that you have. It's kind of like pointing two leaf blowers at each other. It just doesn't work well. So it kind of shoots off. But even when you're adding force to the same thing, that's still not great either, which is how we get into like electromagnetism's explanation in this theory. Sorry, I'm just rambling on, aren't I? Really should have had some notes to go on for this, but I'll keep up with where I'm going. So you now have all these neutrons in there, which are essentially like compressed atoms. So I think it's, in my mind, I've kind of already dissected the neutron to be a mini hydrogen atom. And that by miniaturizing some of the atoms and sticking them inside of another atom is the only way to get multiple of them in there in the first place. Because I think that they share that neutron at super close range, and that makes them much more stable. And that it's easier when talking to a real person, you know. Scrap that. That I think that's good enough for now on that. So what makes the protons then? The protons are up and down. And I think at some level that is a different formation of like basic principles where it's like two of one size of whirlpool are sharing a secondary whirlpool that is a different size but similar in strength. Because like an up and down quark aren't like opposites of each other. So like there's anti-up and anti-down quarks that are the opposite and would cancel out. And unless they're perfectly lined up to cancel out, you just wind up with a bigger whirlpool and more displacement. So my thought on that would be that you have two sizes that come together, and all three of those make this big size. I've also kind of been thinking about like gravity waves. And it kind of bothers me because like, yes, gravity is like So gravity is like a displacement towards more space. It wants to move into that more space. And a lot of the times we'll use like a dip as that. And I'm not sure if that is quite right because obviously if matter is a displacement, it is the dip. So if you have more space, it seems like that wouldn't be down. It would almost be more like it's up. It seems like things want to travel up in my theory. But even with a whirlpool, it wants to go down. And I've been playing with this a lot too, because like when, let's say you're adding water to the sink at the same rate it's being drained, and you film it from the side, there should be little ridges on either side of the whirlpool from a slight displacement of the water, where it's slightly higher. So it seems like if you displaced more space, like bread, it would rise. But I think it's almost like the space itself. Maybe I'm thinking about this wrong, where because of the movement, maybe that slight rise is even part of what makes like the strong force or whatever like that, right? Where it doesn't quite want to bridge that gap. I don't know. It's probably enough food for thought now. This is probably a fairly long video. So, if anybody watches this, feel free to hit me with questions or your own thoughts. I would prefer if you don't come back with like, "Oh no, you're wrong," but like come to me with like a frame of discourse so that I'll be more open to it. Uh, if you do have some very obvious holes in the theory, uh, I'd like to hear them. Preferably if you could keep it based on the idea of the model of particles as a whirlpool and maybe not some of my more outlandish claims like, oh, there's no such thing as gluons. There's, you don't believe antimatter exists. Things like that. I would prefer just, some civil discourse. Bye.